Because 1 over f is the focal power, you can calculate the focal power from that as well. It's the same thing. Because you'll be taking your measurements in centimetres, you probably want to use this version because you can use everything in centimetres, then convert it to metres and find a power a little bit later. So you can calculate what the focal length is from that. Don't forget to show your calculation on your pro forma. The other thing that you can do when you're doing that is compare the height of the image to the height of the object. The height of the image divided by the height of the object is called a magnification of that image, and if that's twice as big as that, you get a magnification of 2. Sound okay? And it just so happens that the ratio of the image height to the object height is the same as the ratio of the image distance to the object distance. So this divided by that should equal that divided by that. The negative sign is to take account of the sign convention. Because the image has been turned upside down, then we'd expect that to be a negative magnification. If m is negative, it's an inverted image. There's a bit of explanation of that in the lab manual notes. Should just mention a few things about the uncertainties when you're calculating these. When you're measuring the focal lengths via auto-collimation particularly, we'd want you to get an uncertainty in your answer because we're going to need that a little bit later. You're going to be estimating the focal length via auto-collimation a couple of times, so it's probably a good idea to find the uncertainty in that focal length. You'll have measured it, I think, 4 times, and chances are you don't get exactly the same measurement every time. So just use plus or minus half the range of the measurements that you see in the same unit as that. If you get the same measurement every time, you can use half the smallest scale division of the instrument that you used. Once you've calculated the uncertainty in the focal length, we also want the uncertainty in the power. Because power is 1 divided by focal length, it's a multiplication division calculation, then the relative uncertainty in the power is the same as the relative uncertainty in the focal length. Convert it back to an absolute uncertainty in the power, round it to one significant figure, and round your answer to the right number of significant figures for that. So now we want to try and predict where that image should have been given what we know about lenses A and C and the distance that you set up. To find out where the final image is, you can actually treat these one lens at a time. You can use the thin lens equation for lens A, because you know the object distance was 22 centimetres. You measured the focal length of lens A many times. You can actually calculate what the image distance from lens A is supposed to be. Now, if lens C wasn't there, it would have magnified the image, and you could work out the magnification of lens A using this image distance divided by that object distance minus DIA over DOA, and get that as if lens C never existed. So if we keep pretending that lens C never existed, we would get a lens A forming an image back here somewhere, and we would measure the image distance from lens A back to this point here, as though lens C never actually existed. So we do that. Now, when we've got a system of lenses, the image that's formed by the first lens becomes the object for the second lens. So this image from lens A is now the object for lens C. It's an image and an object, so we call that actually an intermediate image. because it's both an object and an image. It's not the final image in the system that we got on the screen. That's not it. Because as soon as you put lens C in there, these light rays don't meet at that point anymore. Lens C spreads them somewhere else. Now, because the object for lens C is actually the other side of lens C, once you put lens C in, these light rays don't really exist here anymore. This object for lens C is not actually a real object anymore. This is a real object because there was really light rays coming from there. The light rays are supposed to be here, but they're not there anymore. So this is a virtual object. It's on the wrong side of the lens from where the light was coming from. So when that happens, we actually say that that is, in this case, a virtual object for lens C becomes a virtual object, and the object distance of a virtual object is negative when you use it in the equation. So there's trick number one. Trick number two, the actual distance of the object from lens C is not this distance, right? Thinking about it. The object distance from the object back to lens C, backtracking against the light, is not the same as the distance of the image from lens A. They're different by this much. So you can use the thin lens equation for lens C just like you did for lens A, but remember the tricks. Firstly, the object distance is equal to the separation minus the image distance from lens A. No, it's not. The object distance from lens C is the image distance from lens A minus the separation of the lenses, right? But because it's a virtual object, make sure that it's a negative number. And don't forget, you're using the focal length from part B of lens C. You measured that already. Because it's a diverging lens, you expect that number to also be negative in your formula. So they're the tricky bits of the calculation. Once you've got over that bit, you can calculate the magnification of lens C, like you did before, using the image distance from lens C and the object distance from lens C. Don't mess up the signs. Remember what sign each one of those is supposed to be. And you can compare your calculated image distance with your measured image distance and your calculated, so your measured magnification with your calculated magnification. The overall magnification, when you've got two lenses, you just multiply the two magnifications together. Get the magnification of lens A, the magnification of lens C, multiply them together, and you should get the right answer very roughly. Very roughly, I hope. Good luck with L22.